Okay, so let's talk about building your own agents, right? Something that we are all at least thinking about, if not doing already. So before we start building our own agent, let's talk about why do we want to build our own agents in the first place, right? Because when you look at it, you can say, hey, LLMs or large language models, they already know everything about everything, right? They have the whole internet as their knowledge base. And if you look at existing agents, I will call them client agents, like Cloud Code or Cursor or whatever you're using, you can already conclude, maybe, who knows, that agents know how to do anything you want them to do, right? But that's wrong on quite a few levels, right? And before we get into that's wrong and why it's wrong, let's take a look at the architecture of every single agent you see right now. Every single agent follows the same architecture, no matter whether you use third-party agents or your own agent, the agents you're going to build and which we are going to discuss later, right? This is very high level for now. So we have an agent. Agent is just code, right? It's code. It's a kind of a server code, right? And then we have a user, that would be you, that sends something to that agent. That agent has no intelligence, zero intelligence over there, right? And that user input is combined with the system context. That's where we describe how agents should behave. Kind of, you're a nice agent, right? You don't yell back at the person who sent you something or whatever. Like you're a software engineer, you're an operator. That's a system context that set the scene for that agent, and then that is combined with user input. And all that combined is sent to large language model, and large language model might, very often, most of the time, will not respond back directly, right, to the agent. It will say, hey, for me to do something, whatever you ask me to do, I need to request execution of some tools. And then that request is sent back to the agent executes that tool produces some response, and then LLM and agent go into some kind of a dance in a loop, but actually they repeat that process over and over and over again. Now execute this, now do this, now do that, until LLM has everything it needs, right? No matter whether everything it needs is to do something for you or to respond to your question or both or whatever it is. And once you did that, and we call that agentic loop, right? It goes in a loop requesting execution of the tools to get the context it needs or to perform the operations it needs to perform. And then we get the response from LLM and to the agent, and agent responds back to you, right? From your perspective, there is only agent, that's who you talk to, but behind the scenes, those are different components involved in it. This is very high level. This is how every single agent worth using is doing stuff, right? Now, the question over there is, from this picture over there, what is really missing? Why would we go beyond that? Because this architecture is what you get by simply installing Cloud Code or Cursor or Open Code or whatever you're using, right? And what's missing really is, first of all, your knowledge. The things that you have in your brain and that agent is not aware about, right? And that's usually what people characterize these days as hallucinations. You hallucinated. And the real response is that it's not that it hallucinated. Most of the time it doesn't anymore, but it has no idea what you know, right? Because that's not on internet. That's in your brain. Then we are missing company knowledge. Your runbooks, your rules, your policies, all the things that make your company do things differently than what is on Stack Overflow, let's say, right? It needs access to your system to do and by system I mean not only both for operations to do something, and to your system in terms to gather some information, whether that system is Kubernetes or cloud or it's wiki pages or whatever it is. And finally, we need some kind of observability to understand actually what is happening behind that, because you send a request to an agent and there are gazillion things are happening there, and if you don't know what is happening, we cannot control the system, any system, and that includes agentic system as well. So those are the four major things that we need to provide to our agents, custom or not custom, in order for them to do the right thing. Right? Without those, we are either not in control, or either we don't know what is happening, or it's not doing the right thing. Right? So let's go slightly deeper. Right? System context, and this is where, and now from now on, everything I'm talking about is from the perspective of custom agents you make yourself, right? And the first thing you probably need to think about is the system context. And the system context is the information that you're going to provide to LLM every single time for a given agent, right? For a given task or type of task, let's say, right? And system context does not have to be static, just to be 100% clear. It can be dynamic, and it can contain anything you want. And that anything could be, company-wide policies, those generic policies, not specific to specific operation, but generic policies from the company, team-level conventions, for example, or preferences of a specific user who connected to that agent, right? Depending on who is connecting, who is using the agent, preferences might be different and so on and so forth. This is infinite amount of permutations you can have there, but the point is that you want to construct that system-level context, that initial context provided to LLM, together with the user input and the access to the tools, which we are going to discuss later, right? So you need to figure out how do you construct the right context at the system level, at the initial level, if you wanted to do the right thing, right? It's fine if you use generic context, but that will not get you very, very, very far, right? And then we need to think about tools, right? How do we provide tools to the models, right? And models, LLMs, by the way, just to be clear, they know if you don't give them tools in a specific way, they assume no tools, zero tools, nothing. I cannot do anything, right? And the way we provide those tools is there are actually many different mechanisms. Tool can be baked into an agent, tool can be MCP, tool can be a skill, tool can be many different things, and they all follow the same pattern. And that pattern is that we provide, when we send the first initial system context to LLM, we send the description of all the tools that are available at his disposal, right? And that description is something like, hey, you can execute kube control, right? And kube control is used for this and that. You can execute this, you can execute that, right? And those tools can be generic, can be made by you, can be hand-coded by you. It can be anything you want. You're in control of what the tool is, and more importantly for LLMs, what the description of the tool is, what it does, why it exists, and how it should be used, right? And once you do that, then LLM starts requesting from the agent, okay, so execute this tool with those parameters and execute that tool with those parameters and so on and so forth. That's the agentic loop that I mentioned before. And then agent executes those. So LLMs don't execute anything. They can only send text messages back to the agent. Agent gets the message, oh, you want to execute this tool? Cool, I'm going to do it. I'm going to execute it and do whatever you ask me to do, right? That's one mode where LLM controls the execution through the agent of certain tools. But there's much more to that when you build custom agents. And much more means that you can have some deterministic tools that are always executed independently of what LLM wants or doesn't want. It could be, hey, I can maybe set some rate limits to things. Maybe I will log the execution of tools that you ask me, and so on and so forth, right? Those are the tools that are executed by your agent without LLM instructing it to do something. That's what you control from the code itself. And finally, there are typically you would have some validation tools that would, for example, obfuscate or confidential information from the execution of your tools, right? Or whatever that something is. Okay, now, and that brings us to one of the most important tools that you will have, and that's semantic search, right? And that's how, besides the system context, the initial context, that's how we provide the knowledge to LLM, right? And knowledge is, think of it like just-in-time knowledge. It's not that I'm going to give you all the information that exists from my company or me, because that would be overwhelming. It's the knowledge that is required for a specific task. And we're going to see in a moment how that really works. But before we actually can give any data, any information to LLMs, we first need to ingest the data. So we get different sources. Like in this case, in this diagram, you have Git repos and Notion and Slack and Jira. It could be anything you want, right? So there are different data sources. And we create ingestion pipeline. We have some kind of a pipeline, a controller that would be ingesting that data continuously nothing to do with LLMs at the moment. And whenever they first ingest all the data that exists, then keep updating, ingesting new data as they're coming, right? Let's say that you're ingesting Slack transcripts. Whenever there is a new Slack call, you would trigger that ingestion pipeline that would put it to the database. But we don't put the data to the database directly, right? What we do is that we create embeddings. Embeddings are a way how to convert text data into the into numbers, essentially. Multi-dimensional numbers, thousands of dimensions of numbers, right? So we convert that into numbers, and the reason why we're doing that is because then we can, as you will see later, search by proximity. Hey, there is a word database, and that is number X, whatever that number is. And when somebody search for DB, which is not the same as database, we can find by proximity that those two are somehow close to each other, so they should relate to each other. We should be able to find them. Anyways, we create embeddings, we convert it into those numbers and put it into vector database. And it sits there, it waits for it. And then comes the retrieval of that data, which is when an agent asks for something, when you ask agent for something, and then, hey, deploy my database. And then you want to search for all the data, for all the knowledge that is close to meaning of deploy database, right? And we do that by, again, creating embeddings. Those are very, very light models, very cheap. Again, converting it to numbers, to put it in a very simple terms, and send it to vector database. It finds records that are very similar to what you're looking for, not the same, similar, proximity, and then it returns back to the agent, and agent knows, okay, I found these 3 documents or these three chunks, what we call, that are related to deployment of the database. Now I know how you deploy databases in your organization, right? And it passes that to LLM. LLM all of a sudden extended its knowledge and knows how to do it within the context of your organization. Cool. Now, once you figure that out, right? Context, system context, tools, and then knowledge retrieval, we can talk about orchestration of multiple agents, right? Because what you will probably have and do is that you will have some client agent like Cloud Code or Cursor or Windsurf or whatever you're using, which are absolutely awesome, right? And you want to extend the capabilities of those agents, those third-party agents or client agents, with your specialized agents and say, okay, cool. You can do everything, but when it comes to this specialist type of operation, call my agent, because that agent knows exactly how to deal with that situation, right? And that's when you call your agents, and normally you would do that through MCP, which is not necessarily designed to talk agent to agent, but happens to be the one that is most used today. And then your Cloud Code knows how to do something. It actually doesn't know even how to do something. Then your Cloud Code or Cursor or whatever you're using can delegate that specific type of task to your specialized agent, the one we discussed earlier, that will be better equipped through tools, through knowledge, through whatever it is to perform that specific operation. And once you create your custom agents and say, hey, others can talk to me through MCP, then basically you have no limit at that point, because you can just provide different communication interfaces to that agent and say, okay, so not only that other agents can talk to my agent, but other applications can talk to my agent, whatever those applications are, or some web UI can talk to my agent, or anything can talk to my agent. Because at the end of the day, talking to an agent is just making requests to that agent, like any other server, client server type of architecture, except that we have different protocols depending on what we need. And most of the time, you will need 2 of those. You will need MCP, which is well suited for agent-to-agent communication, even though it's not designed for that, and REST HTTP for everything else. And then you get into the mesh and the shenanigans that once you start doing that, you will start connecting different agents to talk to each other, some of them being on your laptop like Cloud Code, some of them being web application, some of them being agent code in your cluster talking to some other agent, and so on and so forth, right? And that has a lot of benefits, right? Because most of the people at the beginning of their journey with AI, they think of themselves like being single entity. Where everything works on your laptop, which is great. But once you start moving into organizational setup, company setup, you want to have all those things except the client, except Cloud Code, essentially, running remotely somewhere, right? And that's why those communication protocols are extremely important, because you want to have 1 or 2 or 1,000 different specialized agents and different tools attached to them and so on and so forth, managing some remote servers so that you can manage them correctly, right? That you can upgrade once and everybody benefits from it, and all the other good things that we know about running servers remotely is running them in our own laptops. Okay, and that brings us to security, observability, and cost, right? Which are probably not the things you start with, but are almost certainly the things where you end at the end, right? Because just like people, agents connected to LLMs and the knowledge bases and this and that can do many, many, many different things. And we need to somehow make that secure, and we need to make them observable, and we need to make sure that we don't go bankrupt. Those are the 3 goals, right? So when it comes to security, the logic is, when you start thinking about agents as being remote servers, the logic is somehow similar, but not yet completely the same as what you would do with servers in general, right? And that's that LLMs make some decisions. LLMs decide to do something like, hey, I want to execute this tool, or I want to fetch this information from the web, or I want to do whatever I want to do, given the constraints that I have. And the constraints are the tools available at my disposal, right? And then you will put some guardrails on that, so that you intersect those requests between the LLM and the agent, and make sure that actually it is accepted or rejected, just as you would do in any server situation. And that would go through either automatic approvals, which is, hey, if it passes those rules, it can run, or through human approval, kind of, oh, you need to create a pull request for me, or whatever human approvals approve today, right? And that brings us to observability. And observability is probably the trickiest part, simply because it's so complicated. And it's complicated for a reason that we are facing challenges that we never faced before. And those challenges are, first, we don't know what the input is. In the past, we always knew what the input is. You can click this button, that's the input, right? Now we don't know. Input is anything a person types in their client agent. Anything you can type is an input. So it's completely unknown, unpredictable. Then we have outputs that are also completely unpredictable, because we have no idea what LLM will output. We don't know what it will output to the agent to request execution of something, and we don't know what it will output back to the user either, right? So input is unpredictable, output is unpredictable. We never faced that situation before, right? Maybe we faced in the past one of those two, but never both at the same time. And the only way we can actually handle that is through some form of tracing, right? If we use OpenTelemetry, or there's now new models coming up, or new protocols, but OpenTelemetry is still the king. We can actually trace absolutely everything. If you put into agent, we don't know what will happen. We have no idea, but we can record every single transaction going in. And we can also record every single, or not transaction, actually trace every single request coming there. And we can also trace every single request going to any of the tools. Those are the things we control. We control the tools or other servers we are connected to, and we control the agent itself, right? Once we start tracing that with OpenTelemetry, we get information. Now, there is not much we can do with that information, because that information is so diverse that a person cannot really make much conclusions with it. But the information is there. And then we can have and that would be a separate topic, separate LLM or separate agent that goes through all those traces, who sees all the intents and outputs and tool executions, and starts grouping them into logical categories and try to figure out what is really happening behind the scenes. Separate subject. For now, what you need to know is that traces are mandatory, right? And if you're doing tracing, you're doing OpenTelemetry. And finally, cost. And this is also where it becomes a bit complicated, right? Because traditionally, with cost, we make decisions. Oh, this server should be running on spot instances, or this server should be big, this server should be small, and so on and so forth. Now we're talking about the cost of something that is not predictable, because it's cost based on user request. User requests something. We don't know what that something is. And that something will be processed by a model, by an LLM. And that LLM can be expensive or cheap or anything in between. And the only way we can somehow do that, we cannot create rules in advance. If you type A, then it goes to cheap model. If you type B, it goes to the expensive model. What we can do is have a very, very cheap model that will classify those requests. So when a user goes and says, do this for me, right? It doesn't start doing that immediately, but it goes to a relatively cheap model that will classify and say, this something should be done by Opus. This time something should be done by Haiku, right? This is an easy thing to do. I'm not very capable of doing things, but I can deduce that this is very easy to do. Doesn't require thinking, go to this model, go to that model, and so on and so forth. And it sounds like an overkill, but it's actually not. Once you start facing bills in hundreds of thousands or millions, even sometimes per month, even, right? So you classify requests and deduce which model should do it. Should it go to a reasoning model that is very, very capable, very, very expensive? Or should we go back to the cheap model who is not very capable, but capable enough for that simple operation? And that's my try to keep it on track, on time. I might have gone overboard. Thank you so much for listening to this. You know how to find me. Working Abound, Crossplema project, there are tools, stuff. Okay. Thank you so much. See you in the next one.